Hello, everybody, and here we are with notes on aldehydes and ketones. um, Hopefully, this works out okay for everybody to understand what's going on. As you're working problems, if you want to, send me an email and ask some questions about where you're struggling. So here, we've already done these in class, but we'll predict the aldehydes form from the following reactions. So in the first one, we get benzaldehyde. In the second one, we reduce the ester down to the aldehyde and we get cyclohexane carbaldehyde. In the third one, we reduce it also down to cyclohexane carbaldehyde. The fourth one ends up being 2-phenylethanal. Then we have propanal, and then the dialdehyde. When we cleave the carbon-carbon double bond with the ozone. So those are the aldehydes we can form, and the main ways that we'll form aldehydes in this section. And then we have the ketones, and in the first one we're going to get the 2-pentanone, and then what we remember from org 1, add water across the triple bond and we get the ketone, 2-propanone, 2-butanone. And then here, this one we won't use very much, but we end up adding 1, 2, 3, 4, 5, 6 carbons onto the 2 carbons of the acid chloride. And then we cleave the alkene with the ozone and we get the diketone. Sorry, I need to block this part out. So, if you were to explain to me which is more reactive, an aldehyde or a ketone, you want to think about the one thing you can do for each, draw a resonance structure, where we have a negative on the oxygen, a positive on the carbon, in both, and then think about which one is more stable and why. And we learned back early in org 1 that alkyl groups, the R group, stabilizes a cation. So the more alkyl groups we have around the positive charge, the better, since they both have the double bond O. So the ketone will be more stable than the aldehyde, so it'll be less reactive towards things, just because of the electron-rich the electron-rich carbons we have around it. So based on what we just did, can you draw the addition of any generic nucleophile to a carbonyl? And all we have to do is have the nuc minus add to the carbon of the carbonyl, send the electrons up, and that gives us an O minus, the nucleophile, whatever it was we added, and that. And then from there we add our acid workup and we protonate it, and we end up with this as our product. And the second one here, if we have an acid catalyzed reaction, the first thing we do is protonate our carbonyl because we do not have a good nucleophile, and then the nuc H, whatever neutral molecule, can add into the carbonyl, break the CO double bond to give us this with our H here, and then our nucleophile has a positive charge on it, and then another nuke H can come in and remove that to get us where we've added one nucleophile into the carbonyl. This can continue on, and we can end up replacing the other oxygen with that, and we will draw that again in a little bit, but right now we're just starting with the basics. So here, if we add in 7A, we can add one equivalent of methoxide to our aldehyde or ketone and get the hemiacetal. And the second one, we take the hemiacetal and we turn it into an acetal, and we will draw mechanisms for that as we're going along. And the next one, we take the aldehyde in an excess acidic methanol, and it goes through the hemiacetal that we formed in part B all the way to the acetal, and we'll draw this mechanism on one of the next slides. The next one, we form the geminal diol, and then the last one, zinc, mercury, and HCl. We've done that all along, and all that does is reduce the carbonyl all the way down to the alkane. In F, the first thing that happens is we form the dithiene, and then with Renyi nickel and hydrogen gas, we reduce it all the way down to the alkane, just like we did in the previous example. And the next one is our third way to reduce a carbonyl. The first way on the previous page with HCl was with a strong acid. The Renyi nickel and hydrogen gas is a more milder conditions, and then the hydrazine and hydroxide is strong basic, but they all end up giving us the alkane out of the reduction. In the next one, we get the OH and the CN on there. Here we have a Wittig in I, Wittig reaction, and it is a great reaction to take a carbonyl and turn it into a carbon-carbon double bond. But with the strong base, the N-butyllithium, the first thing that happens is we remove a hydrogen off of our Wittig salt, and then the intermediate there can react with the carbonyl to form a carbon-carbon double bond, where we've taken what was off of the phosphorus off of the Wittig reagent and the carbonyl off of our starting ketone or aldehyde, and end up replacing them and forming a carbon-carbon double bond. The next reaction, the Grignard adds on to the carbonyl. We get the OH, and we have the 3 carbons of our Grignard. The chromic acid, we learned a long time ago, oxidizes aldehydes up to carboxylic acids, and then the peracid here on the last one is a way to oxidize a ketone up to an ester. Now, in that oxidation, we will not have a problem where you have to decide which side of it will rearrange. It will be the same on both sides to make it easy to tell what will happen.